Hey everyone, welcome back to another video by Camroom 5. In today's video, we'll talk about why certain enthalpy values have a negative energy and why certain have positive values. We have talked about the lattice enthalpy a lot, but we haven't considered what's actually happening here and why it's always taken as a highly negative value. So remember, lattice enthalpy was when gaseous ions were combining to make a solid ionic lattice. So imagine the gaseous ions, for example, there are multiple gaseous ions over here which are positive and negative ions, and they are isolated, so obviously there are white spaces between them, and these are like any other gaseous particle would behave. But when they combine together, they try to make a proper ionic lattice which perhaps more or less looks like this. I'm not making it very accurately, I know, but the whole point is that this lattice over here like this has ions in the solid state, which means the particles are tightly packed together. So there are small spaces, or you can say negligible spaces, because the particles are highly close together and now they have made a solid ionic lattice. Because of these attractive forces, which attractive forces are here, so here we have electrostatic forces, because we have already studied it in O levels, electrostatic forces between cations and anions. And these forces of attraction result in release of energy. So whenever there's attractive forces behind, energy is released, so it behaves as an exothermic process. This exothermic process releases energy, and the amount of energy depends on strong attractive forces. So the lattice enthalpy directly relates to the strength of forces between the ions, strength of forces between ions. We talked about another value, which was the solution enthalpy. Remember, we would add some water into the ionic lattice when we would add some water over here, and we would call it the enthalpy for solution. So why is solution enthalpy also negative? Why dissolving the substance in water also behaves exothermically? Because when the ionic lattice goes in water, the ions move away from each other, which is reasonable, right? But there is attraction behind this. You may ask, what attractions are there? It's basically the water particles attracting the ions. Remember, water molecules, which are H2O molecules, they have a dipole on them. The oxygen and the hydrogen atoms in the water molecule have a net dipole because hydrogens are partially positive and oxygen atom is partially negative. So when the solid ionic lattice goes in water, the positive ion is attracted by the oxygen part of the water molecule, because the oxygen atom is slightly negative, it's called partially negative. So the partially negative oxygen atom attracts our cation, and these attractive forces result in release of energy. There are attractive forces between the dipole of the water and our cation. Similarly, the negative ion is attracted also by the water molecule, but this time it is attracted by the hydrogen atoms of the water molecule, like this. The hydrogen atoms, which are partially positive, they attract our anion, and as a result of the attraction between the partial positive hydrogen and our negative ion, these attractive forces also behave exothermically, so energy is released from here also. That is why the solution is also exothermic. And we know the combined effect of hydration, where the gaseous ions go directly into the aqueous state that is already, again based on attraction, so that is also negative. In today's class, we'll also talk about why certain values are more exothermic than the other. So here we will talk about factors that affect the enthalpy of lattice, enthalpy for hydration, and enthalpy of solution, because they are connected in a combined Hess cycle. There are two important factors behind controlling these values. One factor is the charge on the ion, and the other factor is the size of the ion. Since all these values are dependent, like we already said, these values are dependent upon the strength of forces, this leads us to a concept of the Coulomb's forces of attraction. If you have studied physics, or you would be doing it, between the ions, the attractive forces are governed by the Coulomb's law, where the forces are proportional to the magnitude of the charge on cation and anion, and it's inversely related to the square of the distance between them. So you can see it's directly related to the charge, and it's inversely related to the size, because more size means more distance between the ions. That is why the charge and the size both have a vital role to play. If the charge is more, then forces would be more. And when forces are more, the enthalpy values become more exothermic. I repeat, if the charge is more, like +2, +3, then the forces become more, and more forces result in more exothermic values. Similarly, if the size is more, if the charges are bigger, then the forces would be less. Let me write it like this. Forces would be less. And that is why enthalpy values would be less exothermic. They are always exothermic, we should know this. They are always exothermic. This is out of question. But it's about more or less exothermic. Let me give you an example. Let's draw a comparison. My first comparison is going to be between sodium chloride and let's say potassium bromide. If I try to draw sodium chloride, my ions look like this, the positive ones and the negative ones. I have got sodium ions with green and the chloride ions which are orange. But when I try to draw potassium bromide, my potassium bromide will look slightly different. You know why? Let's talk about it. Let's pick some other colors. Let's say purple is for potassium, and let's say bromide is slightly orangish. No, let's pick some blue color. Okay. So potassium is a big cation. Bromide is also a big anion. They look like this. You can clearly see that my ions are really big compared to the sodium chloride ones. The charges are still the same, but the sizes are different, because sodium had a configuration of 288, chloride had a configuration of 288. When you talk about potassium configuration, it was 288, and bromide has a configuration of 288. I'm not writing the exact configuration. The idea is more shells. Since the ions are bigger, on here on the right hand side, size of the ions are bigger. You can say larger ionic radii. But with sodium chloride, you can see smaller ionic radii. So sodium chloride has a smaller ionic radii, and the distance between the nuclei, distance between the charged centers, is less. Here you can see small distance between the charged centers. But here you can see a huge distance between the charged centers. It's a larger distance between the charged centers. With bigger distance, with larger ionic radii, you will have less exothermic values, and with smaller ionic radii, you will have more exothermic values. So one thing we are clear is that bigger ionic radii cause smaller attraction and less exothermic values. Now let's create another comparison. Let's call it comparison 2. Let's call it comparison number 2. The first one was between the sizes. So comparison 1 was size. Now in comparison 2, we'll talk about charge. Imagine sodium chloride and magnesium oxide, or it would be better if we say sodium fluoride and magnesium oxide. Let's pick the same colors. This is my sodium chloride that looks like this. Each one is positive and negative 1, 1. So plus 1, minus 1. When we talk about magnesium oxide, let's say red color and let's say blue color. So here the charges have similar size because they both belong to the same period of the periodic table. But charges are different. Sodium configuration was 2, 8. Magnesium configuration was also 2, 8. So two shells, both have 2 shells, similar size. When we talk about fluoride, the configuration was 2, 8. When we talk about oxide, the configuration was 2, 8, same size. But sodium fluoride have plus 1 and minus 1 ions. Magnesium oxide have plus 2 and minus 2 ions. So here the charges are more charge, which creates more attraction, more attractive forces. And as a result, magnesium oxide would be more exothermic, lattice, hydration, etc. But sodium fluoride would be less exothermic. The charge and the size together give us a value known as charge density. Let me add another sheet over here. These two things, the charge and the size, which are the factors that govern my forces, they give us a value known as charge density. Charge over size is equals to charge density. So if something has more charge, it has more charge density. But if something has more size, it has less charge density. So always remember, these are the two factors that govern the lattice and hydration values. Charge is directly related, size or ionic radii are inversely related. And we call this value as charge density. I hope we are clear. Stay tuned, guys. Thanks.